Okay, so rotational inertia with integration. Well, everything requires either differentiation or integration these days. That's just because the level of physics we're discussing requires that kind of mathematics. So let's start with something simple. We have a bar, a uniform bar, just like we did in center of mass calculation. And let's count the blocks. I think I had 20 blocks for the whole length. Okay, so here's the center. Alright, so I'll put a 0 here, and maybe just redo that. Okay, so we have the center, and the bar has a length L, so it stretches between plus L over 2 and minus L over 2. So we'll assume that the bar has a total mass of m, and that makes the density, which we assume to be uniform, to be mass over length. Okay, m over L. That's the density. And we're looking for the rotational inertia of such a bar. We should already know this value in the previous discussion. So this I through that center mass is equal to 1 over 12 ml squared. Alright, so we're just trying to prove this formula, and that shouldn't be too hard because we have a uniform bar, just like we had a uniform bar for the center mass calculation. So let's recall the formula we have so far. So we know that center mass for point masses. So for a single point mass, I center mass is equal to mr squared. This r is the perpendicular distance from the point mass m to the axis of rotation. Okay, so this does not apply to an extended object like this bar, because different parts of the bar will have a different distance to the axis of rotation. So we don't really have a value to use for r squared. So let's recall what we did in the center mass calculation. What we did was we just picked a small section of the bar and start describing that section. So we'll do the same. We'll just pick a small section. Okay, here's a small section, and this section contains a small amount of mass, small enough to pretend that it is a point mass. So we can use this, and maybe that r will be from the origin to the center of this bar. All right, so this is r from axis of rotation to that center. And if we set up our axis to point to the right and put our origin here, this r also is the same as x. All right, so that's good to know. We have this small mass. We'll designate the mass as delta m, small but not infinitesimally small. And we also have this width, which is delta x, because the x-axis runs along this direction. So a smaller width along the x direction is delta x. So we have this, and that means we can calculate the rotational inertia of this small thing, well, with the mass delta m with the distance. So to turn this into a formula that we can integrate with, this is that formula. So we'll have an r squared and a dm. So the limits will be defining the exact location of the bar. Alright, so we're trying to integrate this, and we found a delta m here just by arbitrarily cutting a small section out of the bar. And we can use limit to push this into dm. So here we have delta m. If I recall this correctly, I related delta m with delta x. So if you have this amount of mass, you have this amount of width. So length times linear density, this should produce the total mass. Alright, so this is equal to m over L times delta x. Alright, so if I apply limit to the left and right hand side, I can get limit delta x shrinking towards 0, delta m. So this is supposed to be called dm now, that we're cutting a very thin, infinitesimally thin slice of that bar. And if we substitute this for the delta m, we'll have m over L delta x limit, so that turns into dx. Alright, so this is an important thing that we did in center of mass calculation. This was the exact same thing that we're also doing here. So we're turning a dm that you cannot really integrate into something that is coordinate related. That is something you can integrate along the coordinates. So this is the first very important thing, to turn dm into a coordinate related quantity, differential quantity. And the second important thing is to figure out this r. We already did it. It was easy. The distance from the axis of rotation to the small point, the small mass, finite mass, or infinitesimally small mass, the distance is just a coordinate x, right? So we know r is equal to x. This is the second important thing. These two things will make the integral doable. So now we can do the integration. So let's start with the integration, maybe right here. So I is equal to the integration of r squared. So now we turn this into x squared. And dm, we're going to use m over L dx. And now we can also specify these limits. Because our bar is between minus L over 2 and L over 2, we should also integrate our dx through that same exact limit. Alright, so this shouldn't be too hard. M over L is a constant, it comes out. And we're integrating x squared, so we get x cubed over 3. L over 2 negative, L over 2 positive. So we'll have m over L, L over 2 cubed over 3 minus negative L over 2 cubed over 3. Right, so minus 1 cubed is a minus 1, so minus 1, this is plus 1, and these two terms are identical when they're added, so twice of the individual term m over L times a 2, that's combining these terms, and then I'm going to cube that, so L cubed over 8 and divided by 3. So you can divide out an L, and you'll have L squared, so mL squared. Alright, so I like that. Everything has a mass and a length squared. And now you have 8 and 3, 24, 2 on the top, so 2 over 24, 1 over 12. So this gives you the expected answer, center mass for the bar sitting in the center. Okay, so just as a practice, now we know how to do this. This is simple. What if we have a bar that is spinning along its end? We know that we can use the parallel axis theorem to figure this out. But since this is integration time, let's go do integration. All we have to do is to place the bar between 0 and L. So now, this is our axis of rotation for convenience, so that any small piece of mass is going to have its distance from the axis of rotation exactly identical to its coordinate x. So that is why I place it the axis of rotation at 0, 0 coordinate. So that's the same exact thing. You'll get the same exact formula. And what is different is these limits, right? These limits. So I'll write it down again. I is equal to m over L x cubed over 3. The limits have changed, and so L 0 to L now. So m over L, L cubed over 3 minus 0 cubed over 3, right? So this is equal to 1/3 mL squared. That was also as expected. Thank you.